Welcome to our first problem for our bearing stresses. In figure 1-1 to assume that a 20 mm diameter rivet joins the plates that are each 110 mm wide. The allowable stresses are 120 megapascals for bearing in the plate material and 60 megapascal for shearing of rivet. Determine A, the minimum thickness of each plate, and B, the largest average tensile stress in the plates. So we have tau is 60 megapascals, and for our sigma sub p or our bearing, 120 megapascal as limitations. So we have here for us to determine where the area that is perpendicular to the load P, it should be where the rivets are, or the maximum number of rivets. For example, if we have 3 rivets and they are aligned all together, that is where we should cut the area. Because if we consider the area where there are no rivets, that would be incorrect, because we are not considering the area where the maximum normal stress would happen, right? Where the area is less, that is where our maximum, that is the limit. So I shaded the perpendicular area with our blue pen, right? So the other area would be the bearing, but let us focus on our P, or our normal. So that is the whole length, the whole width is 110 minus the diameter of the rivet, so we would have 90t. So in here we can see that we have 3 unknowns. That means that would just be an equation. So let us try for our shear. We are given a 60 megapascal. So there is only one rivet and it is a single shear, right? So we will expose as we did in our other examples. For shear, I will shade the area as blue, and I will, since the forces is going, let us try to draw the plate so that we can imagine better. So the bolt should have been at the bottom, but it is still the same. Anyway, I will shade the plate and we can calculate area of the blue, which I shaded, would be a circular area. So for our P, it is of course equals to V, because we are on our single shear. So tau is equals to, it seems that we need to calculate for our V. We can calculate for our V, right? Because we have been given our shear stress itself, or the shear strength. So 20 mm squared. V should be in newtons. Our V is equals to, let's try to use our calculator. 60 alpha equals x 4 multiplied to 20 squared. So solve for x, it is 18,849. That 555 or 56 0.56 newtons. We already know that. So for our bearing, we can use our what we calculated as V for our P sub B. From the figure, we can already see where our bearing is gonna happen from our first figure, or the figure we have drawn when we exposed our normal. But we will try to draw from another perspective so that we can see these arrows. So bearing is the contact pressure between two bodies, right? So the area that gonna resist the rivet, since the plate is the one that is gonna move, the area that gonna resist the rivet would be the one under which I put the arrow on. So if we cut through the middle, we can expose the same area, perpendicular area, as our normal. But the only difference is it must be the body. There must be two bodies that are in contact with each other. Let us try to draw another figure so that we can see the dimensions of the bodies that are separated. So here we will consider the bottom part of the problem. The rivet should be there. So we have our thickness, so let us say the P is going outwards, or at that direction away. It is trying to, it has a tensile force, it is going away. So as you can see, the area of the plate that is gonna resist our rivet would be the blue. That is the maximum. It must be at the middle. Of course, it can also resist at the smaller part of the circle, but it must be at the diameter, so that at the middle of the circle, so that we can consider the largest area. So it is simply 20 times T. Next, we have a limitation, the allowable stress of 120 megapascal for bearing. Since our load is only one, it must be our shear. It is the same, since that's why three stresses can occur in a single structure. These three simple stresses. So we have our thickness. Let us check our units. Yep, the perpendicular area is base times height, which is 20 times T, which are both in millimeters. So we would have millimeters squared. So our thickness is 7.85. So we can calculate for our normal stress already. Let us substitute 90 times T is our area, and our load is the same, as our V and our P sub B. So we would have 26.68 megapascal. That is all for our first problem. Here, our problem number 2. Two 10 mm thick plate members are to be connected using straps of the same thickness and 12 mm diameter rivets as shown in the figure. Determine the maximum bearing stress if the maximum tensile stress on the plate members due to load P is 24 megapascal. The members are 50 mm wide, assuming all the rivets fill the holes. So we need to look for the bearing stress. So here I will draw the bearing and normal stresses in a single diagram, single illustration. So our P, so we will consider the direction of our blue arrow which we cut. So since P is on the plate, we know that our normal would be at the cut where the rivets are. So I will shade the normal as blue. Here we have our diameters, and there are two of them. So they are both 12 millimeter. So we can isolate the separated area, the areas that are separated by the rivets, which is perpendicular to our P. That is where our normal is. The areas that are not separated would be, of course, for our bearing, because at those areas there will be a contact between bodies. That is the location of our bearing. The area that are resisting are perpendicular to P for both bearing and normal stresses. That's why they are denoted by sigma. The only difference is that bearing would mean the contact between two bodies. So we would have here, so I will color our area for bearing, the resisting area for bearing, as red. As you can see, they are both perpendicular. So let us focus on our normal. There are two 12 diameter. So 50 minus 24 applied to 10, that would be 260 millimeter squared as our area. So since we have also been given a 24 megapascal for our limitation of our normal stress, we can calculate for our P or our load. So our answer is 6,240 newtons. Next is for our shear. Since here we can see that we have a double shear, right? For each bolt there would be double shear, and we can observe that the bolts are aligned to another bolt and they are in pair. So our 4 bolts can be divided into 2 at a time because they come in pairs. So the place or the location of where the plate would have the most resistance would be the place where the two rivets are located, because the rivets are trying to hold the plates in place. So the location when we are looking for the maximum shear stress would be where the highest number of rivets are. Of course, for our minimum, it will be the lowest. For example, if we have the same 4 rivets, but the distribution would be not in pair, but there are 3 rivets on the left side and 1 rivet on the right side, the place where the maximum would be at the 3, because when the rivet on the that do not have pair or does not have companion would break, the other 3 would still hold. That's why the rivet can still hold the plate. And when for the minimum, we do not want to break anything, or we do not want failure on every rivet. We would only consider the single rivet that is all alone. So for our problem, let's go back. So we separated the rivet. It is in double shear, and we can simplify it. 2V is equals to our load P. So our load P is, our area is 2 multiplied to our, since we are in double shear, we've already done this a lot of time, we need to equilibrate our equation. So we need to multiply our area by 2. So but here we will multiply again by 2 because we want to know the average. So we are trying to look for the average shearing stress. That means we will consider the 4 rivets. So we will multiply again by 2. So the first 2 is for our shearing formula to be in equilibrium, and the second one is because we want to consider every rivet, because from the illustration that we separated, we only considered a pair, but here if we want to look for our average, we will need to consider our other couple or other pair. But if the question is we are looking for our maximum, then we do not need to consider the other couple. It depends on the question that is being asked. So our 2V, that's why we multiplied by 2, right? Since P is equals to 2V, this we are in double shear. You should already know that by now. We've already done with our shear. So our answer for our average is 13.79 megapascal. So let us try to calculate for our bearing. So for bearing, we already drawn the area that is gonna resist the P by our red pen. So it is the maximum bearing stress. So it would only be right here, the red ones. So it is the same with our example earlier. If we are of 3 rivets on one side and a single rivet on one side, it is the same concept. And you should try to improve your analysis. For that, it is the same. So we are trying to know the maximum, and it is not the average bearing stress. So we have here our area of 240 millimeter squared. The area of the red is simply base times height, and I multiplied it by 2 because there are 2 rivets. So use the same load that we calculated using the maximum tensile stress, since as we can read, it is the maximum tensile stress, meaning the load that we calculated is the limitation for our stress, normal stress, so that the plate will not break. That is why we use our load over and over for different types of stress. We test a certain magnitude of load to our different types of stresses, bearing, normal, and shear. And if ever we are given a maximum allowable stress or maximum stresses, we can use that as a basis. So that's all for this problem. Thank you.